Okay, and now we are going to look at cantilevers, which are actually easier in a way as questions. So, a cantilever, you should probably know, is fixed at one end. Now, strictly speaking, you make the choice on like the x-axis where it is, and you could have it fixed on the right-hand side, and the x equals 0 being the free bit. Just don't do that. You can if you want a bit of crack. If you're finding everything too easy, maybe do that. But for the rest of us, don't. So we'll put a bit of deflection on this one. It's hard to draw them properly. Anyway, so this is a cantilever. It's got some loads, and what we're interested in calculating in the questions is the maximum deflection. Now, if you kind of come and say, hang on a minute, I have a formula for the maximum deflection, but you're kind of missing the point, which is that where those formulas come from, the type of maths we're doing. Now, there's a possibility that I have this picture slightly wrong and that in fact we should be looking at that distance there, but if the deflection isn't that big, they're going to be very, very similar anyway, so we'll just pretend it's this one. So this would be like your delta max. Or I might be calling it the y max. There's possibly one of them is y and one of them is delta in your engineering modules, and I apologize if there's some confusion, but okay, like technically I'm just writing down a differential equation and the maximum of it happens at the span of the beam, and that's what I'm looking for. Whether it refers to this or this, I'm actually not too sure. The derivation of the differential equations would show that, but it's probably a bit harder than what we need to do. Right. Now, there's a possibility when you have a point load on the end that there is a bending moment there, but I'm going to avoid that in this thing. Do I actually mention it? Yeah, so the point load at the end of the beam, I think, would mean that possibly, I think it means that the shear force at the end would be equal to the magnitude of the point load. And then that would be a, not actually 100% sure on this. That's wrong anyway. It shouldn't be the shear, it should be the bending moment. It would be the magnitude of the point load times length, something like that. But of course, listen, we're avoiding it, so don't worry about it. So there's no deflection anyway at the fixed end, so you C2 is equal to 0, easy. There's no slope at the fixed end because it comes out straight, so y dash to 0, which means C1 is 0. There's no bending moment at the free end. Now, alternatively, there's a couple of, okay, there's no bending moment at the free end, so M of L, so the bending moment at L is equal to 0. Now, you can have a UDL there, but a little bit of UDL on its own, just going on the end, isn't enough to cause a moment, but a point load is. That's probably a question for your structural engineering lecturers rather than myself, because I'm not an engineer. I don't know if you caught that yet. Hopefully you have. So this is an initial condition. What that will mean is that the bending moment at A will be negative, but that's okay. So this, remember, these are the positive moments, these are the negative moments, and so the loads are positive, and the wall, which is making the beam go anti-clockwise, they're going to be negative moments, so MA is going to be negative. The other thing you can do for equilibrium, because these are all equilibrium equations, nothing is moving, the bending moment at A must be minus the sum of the moments if you know how to calculate the moments due to individual loads, but that's not always going to do you, because in particular I think the moment due to a uniformly varying load is a little bit different, so that's not really going to be an approach that you take. Look, this is what you're going to do. And the other one is, because there's no reaction force at the free end, yeah, that's certainly true, so that would be that the shear force at L is equal to 0. maybe I won't write that down. But instead just say forces down must equal forces up. So the forces down is the total load, and the force up is the reaction at A. So the reaction at A must equal the sum of the total loads. So here I've got this. Yeah, I'm not. One of these is probably wrong, and I'm not even sure which one it is. They're possibly. They're possibly both right. mg we see would be kilonewtons if you pick the appropriate units, but it's not going to happen. It won't happen, so I won't worry too much about it. It's a good question for. You might have learned about it already, or else in semester 2, what happens to a cantilever when you got a point load on the end, but we're not going to see it. And I said a UDL on the end is no problem. It is clear from the physics / when I say physics, geometry, engineering, I mean look at pictures, think, do engineering, that the maximum deflection occurs at the end. So that's kind of obvious if you just think. And the question that will be given would be to find the deflection at the end of the beam in terms of E and I. It might prove useful to solve with the fourth order differential equation rather than what we've been doing, which is you write down the load per unit length, then you solve the second derivative bending moment is equal to that. You find the bending moment, you stop for a while, then you go off and find the deflection. You can just do it in one go. And then the first two boundary conditions mean that the last two constants of integration are 0. Now we will write them in, just to be clear. Then look at the last boundary condition to find RA is the sum of the loads, and then all you have to do is find MA with this. Yeah. And then just find y of x and substitute in the span of the beam to find the maximum deflection. Okay, so it's maybe there's a lot going on here, but it's actually, you'll see the questions are actually easier. So, find the maximum deflection of a light cantilever beam spans 6 meters with a uniformly distributed load of 36 kilonewtons per meter between 2 and 4. Let's draw a picture. Now, when I draw it, the beam is going to look undeflected. It's just some of my drawing doesn't look crap. It's probably worth commenting that. Now, again, this is something I don't know, but I think that the x equals 0 doesn't start here, but starts here. Well, I know that in terms of the maths I'm doing. So a 6 meter beam here is actually longer than 6 meters. Okay, so the UDL is between 2 and 4. So turn it on at 2, turn it off at 4. Now, you can talk about symmetry here because the supports aren't symmetric. Okay, so let's write down the load per unit length. Magnitude of, sorry, I should write down the 36. So turn it on at 2. Turn it off at 4. And then the differential equation that I'm recommending you use here, which is that EI times the fourth derivative of the deflection is minus load per unit length. So EI times the fourth derivative, that's IV, so it's like 4, V is 5, IV is 4. Minus this, so if you do minus W of x is minus 1 times this, it'll make this minus and this plus, and off we go. I'll probably go at the constants of integration as I go. Fixed constant EI, antiderivative fourth derivative is third derivative. Antiderivative of a u function is square bracket. Fixed constant plus 36, antiderivative of u function is square bracket. And the constant here, the first one is RA. And we'll probably just we'll find it again. So the reaction A, so let's just explain it here again. So if it's an equilibrium, the sum of the forces must be 0. And the up forces is RA, and the down forces is the load. And remember, these, like, this isn't mass here, this is actually weight. Yeah. So the 36 kilonewtons is an appropriate M by G. Now here you've got 36 kilonewtons per meter, so you got 36 there, so it's 72 in total. So you got 72 going down, and for it to be in equilibrium, RA must match that. Because if 72 is bigger, the beam has to go down because there has to be an acceleration. So RA is equal to 72. Done. And this is what we'll anti-differentiate. If you want, you can keep the RAs, and I think in, say, in the marking schemes, that's often what I do. We'll at it again. Fix the constant, EI, and antiderivative of third derivative is second derivative. Fix the minus 36. Antiderivative square bracket is square bracket squared over 2. At this stage, you probably should be able to do the antiderivatives in your sleep. Antiderivative of 72 is 72x. And then the constant here is ma. We could stop and find ma at this point because ei times... Now remember the assignment is open book, so if there's any formula you're not sure about, you can check it, but this is actually equal to the bending moment. This is something we've seen in previous sections. So if you want, you could say at this point, there's nothing causing the beam to do any bending at 6. So if you wanted, you could stop there, apply that boundary condition to find ma, but I think I'm going to do it down here instead. So I'll anti-differentiate again. Fix ei. Antiderivative second derivative is first derivative. Minus 36 over 2 is minus 18. Antiderivative of square bracket squared is square bracket cubed over 3. 36 over 2 is 18. Antiderivative square bracket squared is square bracket cubed over 3. Fix the 72. Antiderivative x is x squared over 2. ma, I don't know yet. I'm just going to call it max. And even though I'm going to say that C1 is 0 just in a moment, I still think you should write it in. Because if you get into the habit of leaving it out, and you do simply support a question, leave it out, you're in a world of pain. C1 is proportional to the slope at 0, and because it's fixed, it comes out straight. Look, that's flat. Slope at 0 is 0. And so C1 is proportional to that, so C1 is 0. And that's also the case for fixed ends and cantilevers, but not simply supported, which I've said enough times now. And I will anti-differentiate again. Fix the constant ei. Antiderivative of first derivative is y of x. Minus 18 over 3 is minus 6. Fix that constant. Antiderivative of square bracket cubed is square bracket to the 4 over 4. 18 over 3 is 6. Fix that square bracket. What am I talking about? That's the constant fixed. But anti-differentiate square bracket cubed to get square bracket to the 4 over 4. 72 over 2 is 36. Fix that constant. Antiderivative x cubed is x cubed over 3. Fix the ma. Antiderivative x is x squared over 2. Now the c1 is gone, as in it's 0. I'll put in the other constant. I think it's good practice to always put in the, because I actually see students who, you're trying to be clever here and leave things out. And eventually what might happen is they start leaving out the R and the MA. Bad news. Bad news, fam. So that's 7019. Sorry. I mean, in this module, C2 is always 0. C1 is only 0 for fixed ends and cantilevers. Right, as we've explained. So now we apply the boundary conditions. R is just the sum of the total load. That's done. 72. You may assume this in future. Yeah, we've done this. Now look at the bending moment at 6, which is the same as EI times the second derivative deflection 6, and it must equal 0. So I'm going to put in m of 6, but I know that these two things are equal. Why? From the theory. If you want to go back to the theory, you'll see it. So the bending moment at 6 is equal to, so I'm seeing minus 36 divided by 2, which is minus 18. Square bracket, 6 minus 2 to be squared, plus 18 square bracket, 6 minus 4 to be squared. 72 plus 72 times 6, plus what we're looking for, that MA. And we know that the bending moment at 6 is 0, so this is equal to 0, so I can write it over here. And I'm going to put in that exclamation mark to kind of signify I want that to equal 0. Now I'm going to just find out what this is. Now there is an alternative, as I mentioned on the previous page, about balancing the some of the forces, some of the moments. So if you do know this theory and you end up with the right answer, I'm quite happy. I'm not happy though to use your theory, which means your formulas, to just find the maximum deflection. But if you want to say, okay, in terms of bending moment, this is the same as a point load of 72 at x equal to 3. So it'll be a bending moment of 216, 3 by 72. So the MA, to balance the moments, because it's in equilibrium, otherwise it's rotating, must be minus 216. So we're going to find minus 216. Or I'll look like an idiot if we don't. So let's find this number here. Minus 18 by 6 minus 2 is 4 squared is 16, plus 18 by 6 minus 2, 6 minus 4 is 2, squared is 4, plus 72 by 6, please be 216, yeah, 216, that's 216, so all I have to actually do is take away 216 from both sides. And you want to make sure that your MA is negative. An MA is positive is not going to happen in this module. If you want to talk units here, kilonewton meters, not per meter. So this means if I simplify this, 6 over 4 is 3 over 2, 36 over 3 is 12, minus 216 over 2 is minus 108, and divide both sides by EI, I get the deflection here at any point. And now what I want to do is, the question is looking for the maximum deflection, that's going to occur at 6. So I substitute x equals 6 into this, and I can call this y max. Y max is equal to the deflection at 6, which is equal to 1 over EI. Again, sometimes I'm going fast, pause me, rewind me, email me if there's something not clear. Because you might as well, subtitles on YouTube as well might be an idea. Although obviously if I don't speak clearly or if I speak too fast, they mightn't catch it, but I don't think my accent is too bad. 12 by 6 cubed minus 108 by 6 squared. You might have to pause me just to catch up with the writing if you're doing the writing as I am recommending. So I'm gonna calculate this number. Everything in the square brackets is positive, so no bother. Minus 3 over 2 by 4 to the 4, plus 3 over 2 by 2 to the 4, plus 12 by 6 cubed, minus 108 by 36, minus 1656. I think that's kind of big. So it's okay, it's about 16 millimeters, because the EI is roughly something like 100. That's okay. So I do want the minus here. A lot of people leave that out, but like the way we do it is that the deflection is plus that way, minus that way. You can change some signs around if you want, and that's fine. But I don't do it like that. So you might see slightly different signs in the equations, like these equations when you construct analysis, but it's just a choice of, I said before, you pick the x-axis, so similarly you pick the signs. So I think we'll get another one in, oh there's the picture, we'll get another one in, another example in. And I might go quite quickly on the second one because I have about 10 minutes. Yeah, I'll go at it. So here's a picture of the cantilever deflection. So that's what the cantilever actually looks like, but the units obviously are all over the place because this was measured in meters and this is measured in millimeters. Okay, let's do the second question. I'm going to do this quite quick, so you might have to pause me. Find the maximum deflection of a light cantilever beam of span 6 meters with a UDL of 48 kilonewtons per meter between 1 and 3 and a point load at 5. So I'm going to sketch an expression for the loading. I'm always recommending the picture. I don't know why you wouldn't do it, because the picture as well can kind of tell you when something's gone wrong. And it can kind of like say, when I'm looking at this, I know that, oh, the slope there is 0, that means C1 is going to be 0. So we've got between 1 and 3, got a UDL, and at 5 there's a point load. And as we said, there's never going to be a point load on the end because things are a bit complicated then. And rather than messing around with the signs, I recommend you write down W of x. So turn on the UDL at 1. turn off the UDL at 3. Have to turn it off this time because it doesn't go to the end of the beam. Plus a point load, which is a delta function at 5. Right. Off we go. EI times the fourth derivative of the deflection is minus this. So if you minus this is minus 1 times this, so that'll be minus plus minus minus plus minus. Off we go. I'm going to probably calculate some things as I go. So as well, we may as well just show it. If you want to find the MA using the method, so the total MA, the sum of the moments, the clockwise moments, this is 96. It's like for the purposes of bending moment, for calculating what you do is if you do the calculation, you get the same thing. It's like a point load of 96 at 2. So that gives you 192. 2 by 96. And then 18 by 5, which is 90. So we're going to get the total moments, the clockwise ones, is 282. So the wall must be in negative minus 282, but that should all come out in the wash. Okay, let's go. Antiderivative of fourth derivative is third derivative. Antiderivative u is square bracket. Guaranteed to make a mistake now if I'm trying to go fast. Antiderivative delta is u function plus a constant or a at this point, which we know is the total load, which is the 48 by 2 plus the 18 kilonewtons, so 114. Now the reason I actually don't do it like this in the notes is because with a linear load I don't think it works the same way. I'm just not sure. I think you have to do bending moment at the end of 0. Okay. Next thing, antidifferentiate again. EI times antiderivative third derivative is second derivative. Minus 48, fix that. I could go a bit faster and do 48 over 2 here, but I think it's good to kind of be consistent. If you're happy to make some shortcuts and get it right all the time and you give me correct answers, I've no bother with that. Fix the 18. Antiderivative u is square bracket x minus 5. Antiderivative 114 is 114x, and we pick up the MA that I'm confident is going to be minus 282, but we'll let the maths tell us that. We go at it again. EI times antiderivative second derivative is first derivative. Well, it's probably worth pointing out that this whole thing is the same as the bending moment, EI times the second derivative deflection. One of the things I'm going to see for me is confusing bending moment and deflection. They're not the same thing. Deflection is the beam being below neutral, and the bending moment is the bending moment. Not the same. Minus 48 over 2 is minus 24, and it's where some of you will lose marks on the second assignment. 48 over 2, 24. Antiderivative square bracket cubed over 3. Antiderivative square bracket squared over 2. Plus 114, antiderivative x is x squared over 2. Antiderivative MA is MA times x. And C1, running out of space here, but because it's fixed on the left and C1 is proportional to the slope, the fixed end means it comes out straight, which means the slope is 0, which means C1 is proportional to 0, C1 is 0. And that's true for fixed ends and cantilevered. And one final antiderivative. Go from the first derivative to the function. Minus 24 over 3 is minus 8. Square bracket x minus 1 to the 4 over 4. 24 over 3 is 8. Square bracket to the 4 over 4. Why didn't I help make some space? 18 over 2 is 9. Square bracket x minus 5 cubed over 3. 114 over 2, I guess, is something like 57. Does that sound good? Antiderivative x is x cubed over 3 plus MA antiderivative x squared over 2, and then you pick up C2, which we know is 0. Okay. Apply the boundary conditions. We've already got C1, C2 and RA, so we're just left to get MA, and we do that by saying that the deflection at 6 is equal to 0. So to deflect, I'm going into this line here. M of 6. Again, apologies if it's quick, that's what the pause is for. So minus 48 over 2 is minus 24. Square bracket 6 minus 1 to be squared plus 24 square bracket 6 minus 3 to be squared minus 18 square bracket. Now everything in these square brackets is positive, so there's no issue, but just beware when you're doing the other exercises that square bracket of a negative is 0. Plus 114 times 6 plus MA must be equal to the bending moment at the end, but there's nothing causing the beam to bend at the end, so that is equal to 0. So all I have to do is just calculate this number here. Minus 24, what do we got? Minus 24 by 6 minus 1 is 5, squared is 25, plus 24 by 3 squared is 9, minus 18 by 1, plus 114 by 6, minus 282, bingo bango, and take that away from both sides. Remember, MA has to be negative. MA is equal to minus 282 if you want kilonewton meters. This means, go back here, 8 over 4 is 2, 9 over 3 is 3, 57 divided by 3 is 19, and MA minus 282 divided by 2 is 141. And now the maximum deflection, we want to substitute in x equal to 6 into this, so I'm going to call this y max equal to y of 6. Remember, if you're a bit confused by the EI, so the E, by keeping the E and the I not as actual numbers, if you change the material of the beam, that's changing the E, or change the cross section, that's changing the I, the math still applies. So the E is the Young's modulus. The stiffer the material in that sense, the larger E is, and the I that is related, it's second moment of area, so changing the cross section will change that. And you can make the deflections bigger and smaller by, you know, stiffer beams in terms of material, stiffer beams in terms of cross section. So what I got? So substituting x equal to 6 into this, because I'm looking for the maximum deflection, and that occurs at the end at x equal to 6. And out of space. Oh, we're very close for another time. 141 6 squared. I have to bang into the calculator. I don't know how long is on the SD cards.